So how in the world do you teach a computer to see? I don't just mean registering a bunch of pixels. I mean to actually understand what's in a picture, to know a cat from a dog or a car from a truck. It's one of the biggest puzzles in AI. Today, we're going to pull back the curtain on the incredible architecture that makes it all possible, the convolutional neural network. All right, let's get into it.
First things first, we've got to understand the basic problem. Why is looking at a picture so incredibly difficult for a standard AI?
Well, the core issue, the absolute deal breaker, is that they're completely blind to the most important thing about any image, its structure. They see all the pixels, sure, but they totally miss the picture.
Here's exactly what I mean. A simple neural network takes this rich, two-dimensional image and just squashes it. It turns it into one long, single-file line of pixel data. And when it does that, all the relationships, which pixel is next to which, what forms an edge or a corner or a nose, all of that is just gone. The context is destroyed. And when it comes to vision, context is absolutely everything. Okay, so how do we fix this disaster? We need a tool that can look at an image while preserving its beautiful structure. And that brings us to the star of today's show, the convolutional layer, and its magic little helpers, these things called filters. What's so amazing here is how simple the idea really is. Just think of a filter like a tiny little detective, a specialist. Instead of a magnifying glass, it's got a grid of numbers, and it's trained to look for one specific clue. Maybe one filter is an expert at finding vertical lines. Another one is a pro at spotting the color blue. By themselves, they're pretty simple, but when you put them all together, you get a whole investigation team. And the way it finds these clues is just with some super simple math. As this little filter slides over a patch of the image, it does a quick calculation. It multiplies its own numbers by the pixel values it's looking at, and then it just adds it all up. That's it. This gives us a single number, a score.
So what does that score tell us? Well, if the little patch of the image looks a lot like what the filter is searching for, say that vertical edge, you get a big positive number, a strong match. If there's nothing really interesting in that spot, the score is close to 0. The filter is basically saying, nope, nothing to see here, moving on. And by sliding this filter across the entire image, we build a whole new map, a feature map, that literally lights up everywhere that specific feature was found.
And here's the really crucial point. One filter finds one tiny feature. To really understand a complex image, we need a whole team of these filters, stacked up in layers. Each layer builds on the last, finding more and more complex patterns, until the network gets a deep view of what it's seeing.
Now, to control this whole scanning process, we basically have two main dials we can turn. The first is called stride, and it's just the step size. How big of a jump does the filter take as it moves across the image? A bigger stride means a faster scan, but you'll get a smaller map on the other side. The second dial is padding, and this is a really clever trick. It just adds a border of zeros all around the image. Why? Well, it lets the filter properly scan the pixels right at the very edge so we don't lose that valuable information.
So here's what that data's journey actually looks like. We start with our 32 by 32 color image. The first convolutional layer scans it, finds, say, 10 basic features, and shrinks the image's height and width. The next layer then takes those feature maps, combines them to find even more complex patterns, and shrinks it again. See what's happening? The image gets spatially smaller, but it gets deeper with more and more feature information. Finally, after all that, we flatten this rich data and pass it to a standard layer that makes the final call.
Okay, so as these networks get deeper and more powerful, a whole new problem pops up. During training, they can become dangerously unstable. It's a famous issue called the exploding gradient problem.
And the root cause is this really tricky thing called covariant shift. Here's the deal. As the early layers are learning and changing, the kind of data they're passing along to the next layers keeps shifting. This means the later layers are always trying to learn from a constantly moving target. It makes the entire system incredibly wobbly and hard to train.
The source material has this fantastic analogy. Think about it. Each layer in the network is like a book in a tall stack. Every time the network learns a little something, it's like a gust of wind hits the pile. The layers below try to adjust, but the whole stack just gets more and more unstable, until eventually the whole thing just collapses. Your training completely fails.
So how do we keep that tower of books from falling over? The answer is something called batch normalization, and it's a beautifully simple idea. After each layer does its thing, this extra step just recenters and rescales the data that's being passed on. It's like putting little shock absorbers between each book, making sure no single shift can bring down the entire pile. It keeps the whole learning process smooth, stable, and efficient.
Okay, great. So our network is stable now. But, believe it or not, that's only half the battle. Now we have to make absolutely sure it's actually learning the patterns, and not just memorizing the pictures we show it. This is the classic, age-old problem of overfitting.
Here's another perfect analogy. Think about studying for a big exam. A good student learns the core concepts, right? So they can solve problems they've never even seen before. But a student who overfits, they just memorize the answers to the practice questions. They'll ace those. But when the real exam comes with brand new questions, they're toast. We want our AI to be that first student. We want it to learn, not just memorize.
And the solution for this is a really clever technique called dropout. During the training process, we randomly tell some of the neurons in the network to just take a break, switch off. They don't get to participate in that round of learning. Now, I know this sounds totally crazy, but it forces the rest of the network to build a much more robust and flexible understanding. It can't become over-reliant on any single neuron, so it's forced to learn multiple ways to recognize things, which makes it way better at handling new images it's never seen.
All right, let's put it all together. We've got our convolutional layers to see the structure. We have batch normalization to keep things stable, and we have dropout to make sure it's actually learning. Let's combine all of these into our final high-performance model.
So here's the final blueprint. We stack 4 powerful convolutional layers, and after each one, we add batch normalization to keep it stable. Then, we have our dense layer to interpret all those features, we throw in a dropout layer to prevent any memorization, and boom, our final output layer gives us the prediction. Every single piece here has a critical job to do.
Now, before the big reveal, let's remember where we started. A basic network with none of these tricks, trying to understand these exact same images, only managed to get an accuracy of 49%. That's not much better than just randomly guessing. And, with our new and improved architecture, 71.5%. That is a massive leap in performance. I mean, that's the difference between an AI that is completely lost and one that is genuinely starting to see the world.
And this, right here, is the big takeaway. That huge jump in accuracy didn't come from some kind of magic. It came from smart, thoughtful engineering. We gave the model tools to see structure with convolutions, to stay stable with batch normalization, and to truly learn with dropout. Each component solved a specific problem, and together, they created something incredibly powerful.
So we've done it. We've built a network that can actually look at the world and start to make sense of it. This very technology is the foundation for everything from self-driving cars to analyzing medical scans. It really makes you wonder, though. Now that we've given machines the power of sight, what other human senses, what other kinds of understanding should we try and tackle next?